In this video, we'll be learning about the Doppler shift, and we're going to start off by watching a clip from The Big Bang Theory to get an idea of what it is.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
A choo-choo train?
Close. Meow.
A brain-damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
So as we learned from the video, the Doppler effect is the apparent change in frequency of a wave caused by relative motion between the source of the wave and the observer. So for this first example, we have the source, which is the ambulance, and we have 2 observers, one where it's moving towards and one that it's moving away from. But because the source isn't moving, and either are the observers, there is no Doppler shift. Moving on to this example, we can see that the source is now moving away from the person with the headphones, which spreads out the frequency that the waves are hitting him. So this means that he will hear a lower frequency. Now he's moving towards the guy on the right, and this is adding speed to it, which means that when the sound waves get to him, he will hear a higher frequency. In this third example, we have the source in the center that isn't moving. And then we have 2 observers that are moving towards and away from the sound. So you have Wile E. Coyote, who is running through the sound waves, which means he will hear and register them at a higher frequency. Then you have the Roadrunner, which is running away from the source, and he will hear a lower frequency. All right, so here's an opportunity to practice the mathematical application of Doppler shift and how we can calculate it using these equations. So the one on the top left, as you can see, is used for a stationary source and the observer is moving. So this is just like our last example. This is like Wile E. Coyote running towards the speaker. The equation on the right is in reference to the second example. This is where the ambulance is moving, but the observers are stationary. And so then you see the plus and minus signs. For the stationary source, what the plus and minus is representing, the plus sign is for a motion that is towards the source, and the minus sign is for a motion that is away from the source. For the equation on the right, where the source is moving and you have a stationary observer, well, the plus and minus signs mean the opposite thing. So the minus sign means that the source is moving towards the observer, and the plus sign means that it's moving away from the observer. And so let's look at this example problem here. We have a train that has a 150 hertz horn that is moving at 35 meters per second. And it says that the speed of sound is 340 meters per second. So the questions that it asks is, what frequency are observed by a stationary person at the side of the tracks as the train approaches and after it passes? So this is asking for the frequency in the second example that I gave for the person that would be in front of the sound and then the person behind the sound. Then for part B, it's asking what it is for the engine that is currently on the train. So as we do this, first let's pull out what we know. So we have the frequency of the source is 150 hertz. We have the speed of sound is 340 meters per second, and that the speed of the source is 35 meters per second. We know that we're looking for the numbers when it's going towards the observer and away from the observer. And so now we can use this to figure out which of the two equations we should use. Because it's the source that's moving and the observers are stationary, we know we're going to use the equation on the right. And then we can just plug in the information that we've been given to find the frequency that's observed by the stationary people. So here's that all laid out. And as you can see, that when it's negative, you have it going towards the observer, and as you mentioned previously, they're going to hear a higher frequency. And so you can see that that is kept the same in this scenario. And then for part B, what's going to be important to understand is that the engineer is moving with the train. So this means the source, in reference to him, doesn't have any different speed or velocity. And so for that calculation, it'd be 150 hertz times 340 divided by 340, which is just 1. And so because he's moving with the source, he would hear the source's frequency, the same frequency. And so that would leave you with 136 hertz. Now, it's also important to note that this doesn't just apply to sound, but this applies to all wavelengths, so that includes light. So if we look at space, for example, we see all these different colors of stars, and while that can be due to the star itself and the heat, it can also be due to its motion. So let's just take a quick look at that. So in this simplified version, we can assume that they're running incredibly fast for this to work, and you have the coyote who is running into it. So he has an increased frequency, and he would see something along the lines of a blue light, a high frequency light color. And the Roadrunner would be running away, so they would see less frequency, which would give them a low frequency wavelength color such as red. So that's the Doppler shift. That's how it applies to lights, sounds, and all sorts of waves. Hopefully that made sense. And thanks for watching. Thanks for watching.